We are back for part 6 of module 3, where we're going to be looking at CP and CV and how to apply it for gases, and looking at how we can work out our systems and do some example problems to find the heat transfer by applying the first law. So for gases, we don't really have any shortcuts to define CP and CV separately. So for gases, we can say, if we remember, our definition of CP is equal to dH over dt, and our definition of CV is equal to du over dt. And if we rearrange this equation and integrate both the equations, we finally get that we have H2 minus H1 would be equal to Cp multiplied by T2 minus T1. And U2 minus U1 would be equal to Cv times T2 minus T1. And so that's just rearranging the equations. And now, so we can say that for gases, we have two separate equations. So in solids and liquids, remember we had an equation that said C times T2 minus T1 was equal to H2 minus H1 and equal to U2 minus U1. This is not the case in gases, because in gases we don't have incompressibility. So we can't get rid of some terms in the equation as we did earlier. And we always remember that we have to use, just like in solids and liquids, we have to use Cp average at the average temperature, and in this case also CV average. Okay, and the best way to learn how to do these, how to apply this to gases, since we've already derived the equations and looked at some solids and liquids, is to do some example problems. So we're going to be doing 3 example problems in this section, and we're going to start with the one below. So a piston cylinder device contains 2.2 kilograms of nitrogen, initially at 100 kilopascals and 25 degrees Celsius. So we know we have a piston cylinder assembly, and we know that it has nitrogen, N2, and we're told some information. So we can write state 1. And state 1 says that we have a mass that's equal to 2.2 kilograms. Okay, once again, this is a controlled mass system, so we don't have any change in mass. And we're also given that P1 is equal to 100 kilopascals and temperature 1 is equal to 25 degrees Celsius. Now, the nitrogen is now compressed slowly, so we know the nitrogen is going to go, the piston is going to go down. The nitrogen is compressed slowly using a polytropic process during which PV to the 1.3 is equal to constant. So we can say that we have a polytropic process, and we're given that PV to the 1.3 is equal to constant. And so that means that N is equal to 1.3 according to our polytropic process law, until the volume is reduced by 1/2. So we have some extra information. We're told that the volume at state 2 is 1/2 of volume 1. So we have that information. Now, we don't really know the volume at 1 yet, so we're going to have to figure it out if we want to find the volume at 2. Okay, so let's look at the system. It says to determine the work done, so we have to determine the work done, work boundary, and we have to determine the heat transfer in the process, which is Q in. Okay, so these are our 2 things we have to find. So we can go either way. We can start by finding Q in, or writing the equation for Q in and then finding all the terms, or we can do it the other way where we find work first and then find heat transfer. It's up to us. So this time what I'm going to do is I'm going to actually start with our closed systemic first law. So I'm going to write the first law, and then we're going to find all the terms in the equation. Okay, just so we start a little bit differently than last time and start with the overall problem, which is to find the heat transfer in the process. So the first law for a closed system, okay, with control mass, so mass does not change, is equal to the following. We have Q in minus work out, which is our work boundary, is equal to delta U plus delta kinetic energy plus delta potential energy. And some of the assumptions we can make in this problem are the following. We're not given any information on kinetic energy, therefore we're going to say that the change in kinetic energy is equal to 0. And the change in potential energy is also equal to 0 because we don't have any information. Some of the other assumptions we're going to make is that we know we have nitrogen and we don't have tables for nitrogen really. So we're going to assume that we have an ideal gas. Okay, so we're going to assume ideal gas, and if we assume that P and K are 0, we can cancel these out from the general equation. So we're left with Q in minus work out is equal to delta U. So essentially to find Q in, we have to find work out and delta U. Okay, so we can start by finding work out, and then maybe we'll find delta U after that in a second instance. So how are we going to do this? So let's try and find work out. So we know that the work boundary out for a polytropic process the work boundary out is equal to integral of P dV. And for a polytropic process, we have that it's equal to P2V2 minus P1V1 over 1 minus N. And this is for N is not equal to 1. Okay, N is equal to 1.3. Therefore, we know that our polytropic process equation for work boundary is P2V2 minus P1V1 over N. Now, so far, we have pressure 1. Okay, so we have pressure 1. Do we have pressure 2? We do not have pressure 2. Okay, so we do not have pressure 2, so we are looking for pressure 2. We can find volume 1, so we don't have volume 1, we don't have volume 2, and we have N. So let's try and find the volumes first, and then we'll go ahead and find the pressure. So how do we find the volumes? Well, we can use ideal gas equation, right? At state 1, if we use the ideal gas equation, we can find volume 1. So we can say P1V1 is equal to M R T1. And we have pressure, we have temperature, we have the mass. We're only left to find R, and then we can find V. So we can say that V1 is equal to M RT1 over P1. And we can then find R. So from table A1, we can find R. R is equal, so let's go to table A1. If we go to table A1, we have that R is equal to 0.2968. This is the gas constant for nitrogen, which is already underlined. Okay, and then we have all the terms. So we're just going to write the terms out. So mass is 2.2 multiplied by 0.2968 multiplied by 25 plus 273. Remember, you have to convert to Kelvin. Very important. and divided by pressure 1, which is 100 kilopascals. Now, you get here 1.946 meters cubed. And volume 2, we know, is equal to volume 1 divided by 2. It's given in the prompt of the problem. So we can say that volume 2 is just equal to V1 over 2, which is 0.973 meters cubed. Okay, so now we have V1 and V2 in the above equation. We're left to find P2. So in order to find P2, we can do it a couple of ways. We have to figure out P2, and we don't really know temperature 2. So we have two equations. We know that P2 is V2 is equal to mRT2, and we also know that P1 V1 to the 1.3 is equal to P2 V2 to the 1.3. This is from our polytropic process. So we have these two equations, and we have to find what pressure 2 is. Now, if we look at our ideal gas equation, we're missing temperature 2, so it's going to be very hard. We have volume 2, we have mass and R, but we're missing temperature 2, so we can't really find pressure from that equation. However, from this equation, we can find it. We have all the other terms except for P2. So we can say that P2 is equal to P1 multiplied by V1 over V2 by rearranging to the 1.3. And we know that volume 1 is double of volume 2. So we know that since volume 1 is double from volume 2, we can say that this is 100 multiplied by 2 to the 1.3. So we have the two volumes. You can also put them in, 1.946 over 0.973, and you would get 2 as a value. And so we get that P2 is equal to 246.2 kilopascals. Once we have that 246.2 kilopascals, we can now find our work boundary by plugging into our equation. So we have our work boundary is equal to P2 V2 minus P1 V1 over 1 minus N, and that would come out to minus 149.9 kilojoules. Okay, so our work boundary is negative, and it makes sense. The system is being compressed, so the work boundary is negative. Okay, we always remember that work boundary is negative when it is being compressed. Okay, so that's step 1 of the question. We found work boundary. The next step is to find Q in. So let's write our equation again. We have Q in minus work boundary out, okay, it's work boundary out or work out, is equal to delta U. And now we're going to focus on delta U. So since we don't have tables, we have to find U in a different way. So we're going to use CP and CV. So we're going to say delta U is equal to mass times little u2 minus little u1, okay, specific u2 and specific u1. And that, if we go back to the equation we wrote at the start of class, is u2 minus u1 is equivalent to CV times T2 minus T1. So if you have U, you always use CV T2 minus T1 for gases. So we're going to write down the equation. We have mass times CV times T2 minus T1. Now, we have a couple of terms. So we can summarize what we have. So we have T1 is equal to 298 Kelvin. Okay, it's 25 plus 273. T2 is unknown. And we know that we have to find CV at the average temperature. Okay, so we discussed this in part 5, and it's the same here. So the first thing we can do is say, let's look for temperature 2. So using the other equation, the ideal gas equation, we can now find T2 because we have pressure 2. So we can say that P2 V2 is equal to M RT2. And we can rearrange the equation to find temperature 2. And we find that temperature 2, by plugging in the values, would be equal to 366.9 Kelvin. So that means that CV should be found at a temperature that is average between 298 and 366.9. So that temperature is 332 Kelvin. So we know we're looking for a CV at 332 Kelvin. So now we're going to go to table A2. We're going to go to table A2 and find what our CV could be. So we have different tables, and in this case, we're going to be looking for table A2, and specifically table A2 for ideal gas specific heats for common gases at various temperatures. So it's going to be A2B, okay? And we're going to go to nitrogen. And we see that we're given some information for nitrogen at different temperatures in Kelvin. So just remember that this is Kelvin, okay? So we know that we have to find CV at 332 Kelvin. So if we go to 332, there is no value for 332, but we're going to use the closest value. We do not need to interpolate. Okay, remember that we just look for the closest value and we're going to use it. So we're going to use the value of 350. Okay, 350 is the closest to 332. And we get that CV, so if you look at the top here, we have CP and CV. So this is your CP. We're not using this one. We're going to be using CV in our case, okay, because we're looking for internal energy. So CV is equal to 0.744. So we can go back and we are going to write that CV is equal to 0.744 kilojoules per kilogram Kelvin. And now we can solve for our solution for delta U, essentially. So we have our solution for delta U by the equation. So we can rewrite the equation for the first law. We can rewrite it as Q in is equal to delta U plus work out, and that would be equal to mass times CV T2 minus T1 plus work out, and now it's just about plugging the values in. So we have this is equal to 2.2 times 0.744 times 366.9 minus 298 plus negative 149.9. So just be careful with your signage. You keep the work as negative throughout. So we get that that is the case, and we finally get that our Q in, so our Q into our system is equal to minus 37.2 kilojoules. So if we have a Q in that is negative, that means that the heat is going out of the system. And it makes sense, right? Our piston cylinder assembly is being compressed, therefore it makes sense that the heat is going out of the system and not into the system. Okay, so that concludes our first example problem for this session. Now, we're going to look at another example problem. And the next example problem is going to involve a spring. So we're going to be looking at how we can use a spring with, again, an ideal gas system with helium this time. So we have a spring-loaded piston cylinder, contains 5 kilograms of helium as the system is shown in figure 4.77. The system is heated from 100 kilopascals and 20 degrees to 800 kilopascals and 160 degrees. Determine the heat transferred and the work produced by the system. Okay, so same process as before. First, we can make some assumptions. We're going to assume ideal gas because we have helium, and we're going to assume that delta KE and delta PE are both equal to 0. And we can write our state 1 and state 2 of our system as P1 is equal to 100 kilopascals, temperature 1 is equal to 20 degrees Celsius, and then state 2, we have that pressure 2 is equal to 800 kilopascals, and temperature 2 is equal to 160 degrees Celsius. Okay, so that's our information we're given. We also have that we can find now immediately because we know we're going to have to use it probably. We know we can go to table A1 and find R for helium. So if we go to table A1, we can go find R for helium. So R for helium is 2.0769. Or we can also write it as, because it's pretty close, we can write it as 2.077, okay, kilojoules per kilogram Kelvin. Okay, so that's our R for helium. We also know that the mass of the system is equal to 5 kilograms, which is constant throughout. And now what we can do is we can say, all right, let's write our first law initially so that we simplify it. So we have Q in minus work out is equal to delta U plus delta PE plus delta K, and these two go to 0. So we're left with the same equation as in the previous example. Okay, now in order to find our work boundary in this case, so we can start by finding the work boundary. We remember that we have a spring. So if we have a spring, we have to find the work boundary. We have an equation for this work boundary. The equation is the area under the curve of our PV diagram. So if we draw a PV diagram, we would have a diagram that looks something like this from 1 to 2, and pressure and volume. And the area under the curve would just be this area right here for a spring. So it's a triangle plus a rectangle, and this equation equals P1 plus P2 over 2 multiplied by V2 minus V1. So it should be pretty easy to find our work boundary. So we need to know both volumes and both pressures. Well, we already know the pressures, so we already have the two pressures, so we're left with finding the two different volumes. So to find the volumes, we can use ideal gas. So we're going to rearrange our ideal gas equations to figure out our volume. So we're going to say V1 is equal to mass times R times T1 over pressure 1. And volume 2 is equal to M R T2 over P2. We have temperature 1 and 2, we have mass, we have R, therefore we can find our volume 1 and volume 2 very easily. So I'm not going to go through all the calculations in this example because you should know how to do it now, and it's very similar to the previous example. But by solving for volume 1 and volume 2, you would find that the work boundary using P1 plus P2 over 2 times V2 minus V1, and I'll let you do this in your own time, the actual mathematical calculation, you would get minus 11,163 kilojoules. Okay, and so that means that our work boundary is negative once again. Therefore, we know that our work is negative on the system. Okay, that means that our work out is negative. And if we were to actually plot our PV diagram, so V1 would be equal to 30.427 meters cubed, and V2 would be equal to 5.621 meters cubed. Okay, so those are the two values. So if we were to draw it on a PV diagram, what it would look like is something like this. So it would look something like this. So if we draw the PV diagram, we know our pressures, we know our volumes, we have a different shape than before with this. So 1 is at 100 kilopascals, and we see that volume 1 is 30.427. So we have a point here, 1. And then our point 2 actually has a lower volume of 5.621, but a higher pressure of 800. So we have this curve from 1 to 2. Okay, so slightly different shape than our earlier example on using the same spring. Okay, so different case. So now using the energy balance equation, so going back to our energy balance equation, which is this one here, we can rewrite this at the bottom, saying that Qin is equal to work boundary out, okay, what we have as work out, plus M CV T2 minus T1. Okay, we're substituting for delta U, we're substituting the same thing, MCV T2 minus T1. And we have M, the only thing we're left to find is CV. So as an exercise, we know that the difference between 20 degrees Celsius and 160 degrees Celsius, which is T1 is equal to 20, T2 is equal to 160, we know that the average temperature is 90 degrees Celsius. So we're going to have to find CV for helium at 90 degrees Celsius. So I'll leave it to you as an exercise to go to the tables and try to figure it out, and I'll give you the answer now. CV is equal to 3.1156 kilojoules per kilogram Kelvin. And so finally, we have that Qin is equal to minus 11,163 plus 5, which is the mass, times 3.1156 times 160 minus 20. And Here I'm using degrees Celsius because I can get away with it because it's a change in temperature. If you want to err on the cautious side, you could do 160 plus 273 minus 20 plus 273. But they do cancel out. So whenever you have a difference in temperature, you can use Celsius if you want to. And your final answer for Qin would be equal to minus 8,982, okay, kilojoules. So that means, once again, that our heat is out of the system. Our heat goes out of the system, okay? So we're going to do a third example now using this third example right here. So I'm going to copy it over to our page and we're going to get started on it. Okay, so this is our third and final example for today's lecture and also for this final part of Module 3. So it says that a piston cylinder device whose piston is resting on a set of stops initially contains 3 kilograms of air, 3 kilograms of air at 200 kilopascals and 27 degrees Celsius. So the first thing I want to do is I actually want to draw the system because now we have a set of stops, so I just want to make sure that I'm drawing it right. So we have our piston cylinder, and we're told that our piston is resting on a set of stops. So we have some stops here, which I'll highlight in white, and we know that our piston is resting on that set of stops. And it says that it contains 3 kilograms, so we have a mass. So I'm going to write state 1 on the just on the right of this, just to explain it. So we have mass is equal to 3 kilograms, and we have that pressure 1 is equal to 200 kilopascals, and temperature 1 is equal to 27 degrees Celsius. Now, it says, the next statement says that the mass of the piston is such that a pressure of 400 kilopascals is required to move it. So it says that you need 400 kilopascals of pressure to move piston up. So clearly at state 1, the piston will not move. Okay, so at pressure 1, piston will not move because the pressure is less than this like threshold pressure required to move it. Now, in a second instance, and I'll describe this as air. So in a second instance at state 2, we get that heat is now transferred until the volume doubles. So we now add some heat and we have a state 2 where we say that V2 is equal to 2 times V1. Okay, the volume doubles. And we're told determine the work done by the air and the total heat transferred to the air during this process. Also show the process on a PV diagram. Okay, so once it gets off the stops, so we know that when the heat is transferred, the air and the volume of the air doubles. So that means that the only way the volume of the air doubles is for our piston to move up. And at what pressure is it going to be moving up once it gets off the stops? We know that the pressure at which it will move up once it's off the stops is given as 400 kilopascals. So once it gets off the stops, the pressure will be 400 kilopascals and it'll start moving off the stops. okay? And then the pressure will stay constant. So this is a little bit of a deduction that we have to make, but we can say that it will become a constant pressure system once the piston is off the stops. Okay, so we know that, and therefore we know that pressure 2 is going to be equal to 400 kilopascals. This is the deduction that we have to make that is very important. Okay, you have to be able to make this deduction by yourself when you're doing this kind of problem. Okay, and we also know that from 200 to 400 kilopascals, if we're at 399 kilopascals, the piston is not going to move. The piston will start moving at 400. So we can say that from 200 to 400 kilopascals, as the pressure increases, piston is not moving yet. Once it reaches 400, the piston starts moving. So one of the first things we can do is we can find volume 1 and volume 2. Okay, we can find volume 1 at state 1, and then we can find volume 2 from the ideal gas equation. Okay, the reason I want to find volumes is to figure out what our work boundary is. So remember, our work boundary is equal to the area under the curve. Okay, we don't have a polytropic case. We don't have a polytropic process in this case. So it's just the area under the curve. And so in order to find the area under the curve, we need to know volume 1 and volume 2. So how can we find volume 1 and volume 2? Well, we know it's an ideal gas. And we know that delta KE and delta PE is equal to 0. Those are our assumptions. Because once again, we're not given any information on kinetic energy and potential energy. And since it's an ideal gas, we can say that P1 V1 is equal to MRT1, and we can rearrange the equation to find V1. So we have V1 is equal to 3, which is the mass, times 0.287. That is the R for air, which can be found in table A1. So I'll let you find that by yourselves, but this is table A1, 0.287, multiplied by 300 Kelvin. So if we look at our temperature, we have 27 degrees plus 273 is 300, divided by 200 kilopascals. And we get that volume 1 is equal to 1.29 cubic meters. V2 is now double that. We're given in the question that V2 is double. So V2 is just 2.58 meters cubed. So now we can draw a PV diagram, and then we'll be able to solve for work boundary. So if we draw a PV diagram of our problem, we have pressure, volume, and we know that pressure 1 is equal to 200 kilopascals. We know that pressure 2 is equal to 400 kilopascals. And we know that volume 1 is 1.29 and volume 2 is 2.58. So we have a 0.1, which is here, and 0.2, which is somewhere there. How do we get from 1 to 2? So remember, in our deductions that we made, we said that constant pressure will hit once we hit 400 kilopascals. And we also wrote that from 200 to 400 kilopascals, the piston is not moving yet. So piston is not moving, it's not doing any work. So that means that from 200 to 400 kilopascals, since the piston is not moving, the volume is not changing. So we have this process from 1 to 1B, let's call it 1B, from 200 to 400 without the piston moving at all. As soon as it hits 400, now the pressure is going to stay at 400, because that's the amount required to move the piston. And now we're going to have a movement upwards as we continue heating the system up to double the volume. So we have this kind of shape for our PV diagram. Okay, and this might be a little bit challenging to do, but hopefully it makes sense as you do more and more example problems. Now the area under the curve is now just the area between 1B and 2, essentially. So we're just going to try and find the area under 1B and 2. So that means that since it's between 1B and 2, we know that 1B is at 400 kilopascals. So we're going to have our work boundary out is going to be equal to 400 minus 0. Okay, so it's the top pressure minus the bottom pressure to find the area of the rectangle, multiplied by 2.58 minus 1.29. And so we're left with work boundary out is equal to 516 kilojoules. And in this case, the work boundary is actually positive. And it makes sense because the piston is moving up. The system is doing work on the piston, is doing work on the outside. Okay? Now, going back to our first law equation, now we can work out what our first law would be for the total heat transfer. So using the first law for control mass, we can say with our assumptions that delta K and delta P is equal to 0, we can say that Q in minus work out is equal to delta U, and delta U in this case is equal to mass times U2 minus U1, which is also equal to mass times CV times T2 minus T1, because we have air and we don't have specific tables for air. We're actually going to look at an alternative way of doing this problem where we can actually use a table for air, but air is the only gas where you can use the table and have values for the table. Okay, so we're going to look at that in a second in an alternative way to solve the problem. We can essentially use a shortcut. So we have this equation, and now in this equation, the different things we have to find are CV and T2. We already have temperature 1, but we have to find temperature 2. So temperature 2 we can find from ideal gas. So in the same way as the other problems, we can say that P2V2 is equal to MRT2, and then we can say that T2 is equal to P2V2 over MR, which is equal to 1,200 Kelvin. So we have 300 Kelvin and 1,200 Kelvin. So we can find CV at T average, and the T average is equal to 750 Kelvin. It's the average between 1200 and 300. So CV for this would be equal to, let's go to our table to look it up. So table A2 for gases at different temperatures. We go to air, which is on the top left here, and we're going to look for air at 750, and we find that CV is equal to 0.8. Okay, so we're going to write CV is equal to 0.8. Very easy. We actually had the spot on value here. And then it's just about solving the problem. So we have Q in is equal to delta U, so 3, the mass, times 0.8, times the change in temperature, 1,200 minus 300, plus 516, which is our work. And so we get that the heat is 2,676 kilojoules. And that's our heat in. So this time we know that we have some heat into the system. We have a Q into the system. Okay? And that makes sense. We added heat to the system, therefore Q is coming into our system. Okay, and that solves our problem. Now, there's an alternative way you can do this for air. So for air, And only for air, we can use a shortcut. And the shortcut is not always a shortcut, but it definitely makes it a little bit more precise. But it's really up to you if you want to use it or not. You don't have to use the shortcut. One way to think about the problems is to say, I have a gas, I have an ideal gas, I'm always going to use CV delta T for delta U, and that's it. Now, the other way you can do it is to say, we have Q in minus work out is equal to delta U, which is equal to mass times U2 minus U1. And air actually has tables to find U directly. So just like water and R134A, air actually has a table to find U. Okay, so if you have a problem with water R134A, you wouldn't need to find CV delta T because you already have the term for U in the tables. Well, air has those terms as well. And air is the only one that has those terms in our textbook. So we're only going to be using this trick for air. So if you go to table A17, you will see that in table A17, we can find U values at temperature given. So we know that, for example, U1 is at state 1. State 1 is at 300 Kelvin. So U1 would be at 300 Kelvin. We also know that U2 is at 1200 Kelvin. So we still need to find the temperature for both states in order to figure out our values. But we can go in our tables and find U1 and U2. So if we go to table A17, let me scroll to it. We have ideal gas properties of air. And in these ideal gas properties for air, we have our values for H and U. Very convenient, right? So then we can go find our values for U at 300, which is 214.07, and U at 1200, which is 933.33. Okay, so ignore these here, but the other U would be 933.33. So we have our two values, 214.07 and 933.33. So we have, I'm going to write down the values, kilojoules per kilogram and 933.33 kilojoules per kilogram. And so now we can solve our problem using the values for U and not having to do mCV delta T, but just MU2 minus U1. So we have mass, 3 kilograms, multiplied by little u2 minus little u1, which is 933.33 minus 214.07 plus 516, which is equal to 2674 kilojoules. So let's compare the two values. One value gave us 2,676. One value gave us 2,674. Which one is more accurate? This one is usually more accurate because we use tables. Now, for ideal gases, I'll give you the choice, and for air, I'll give you the choice to use either CV delta T or U2 and U1 from the table. But U2 and U1 from the table might be easier to do because you just have to look up the value. Now, if you have to interpolate for the value, CV might be easier because you just have to find CV and that's it. And then you have T2 and T1. Okay, so it's really up to you. Now, for air, you also realize that you only need to find temperature. So you only need to have temperature, the two temperatures, in order to find U. Okay, so you don't need to worry about the pressure too much. You're just going to worry about the temperature, and that's it. Okay, so module that concludes module 3, and I will be giving um, I will be giving a midterm review on module 3 for our midterm, but that concludes module 3, and you can now be ready to do all the study problems given for module 3. So we'll see you in module 4, where we're going to be looking at the first law for open systems.